Hello, everyone. My name is Elvira Rakova, and I'm from Directing. I'm here today on the ARG Movement platform. We have a very exciting webinar about the heat recovery from air compressor. As you know, it is the huge potential to save energy from our compressed air systems, and usually people think that the first thing to do, especially in cold countries, you see I'm wearing a warm scarf today, is that to recover some heat from the system. And we have today an expert on this. It's Mateusz Barczak from the ASFI. So he's a real expert on the heat recovery. And the floor is yours, Mateusz. So just go ahead, and if you have any questions, you can write in the chat to raise your hand, and then we can see how we can manage the questions during the presentation or maybe after this.
Okay, it's my part.
Yes, it's your turn.
So hello everyone. I'm glad to make this workshop today. Heat recovery from air compressors case study is first of Planet 3 part of presentation. Just as we said, my name is Mateusz Barczak. I'm from Poland, from ASFI. Okay, maybe I can start show some slides. In 2 words about our company. We are a heater guy. We are from heating industry. We come from domestic heating systems. 12 years ago, we established in our company energy efficiency department, and I was appointed to develop it. After 3 months of my work, I have first contact with industrial air compressors. And to be honest, I couldn't believe how energy inefficiency the air compressor process is. I have connected with other kind of energy improve in industry, PD, heat pumps, and solar system, but in my opinion, heat recovery from a compressor is absolutely have to do in industrial plant. Okay, maybe next slide. Few examples of our clients for whom we have implemented installation, improving energy efficiency. We have worked in every production industry, furniture, automotive, of course, heavy industry, medical, food, etc. It's not necessary for us. Today, I will, today, this part of this presentation, I will talk about theory, idea, some kinds of dangerous of heat recovery installation. The rest 2 parts, I will show examples, ways of simply use heat recovery for air compressors, and last part is about success story of an implementation of heat recovery from air compressor. So I know who I'm talking to, and I try to don't waste your time in this part of workshop, but in 2 words about construction of oil lubricated air compressor. So compressor stage, it could be screw or vane. Pressure air and oil go to the separator when where the compressor is separated from oil, and it go to a cooler and pipeline. Is not necessary for us today. Oil from the separator go to thermostatic free valve integrated with filter, and if oil is too cold, it flow to injected valve, or if temperature of oil is high enough, it go to the cooler. So where does the heat from compression process come from? In compression process, the inertial energy of the gas reduced and released to the environment. During the expansion, the internal energy of the gas is increased by taking in environment. So in practice, I know two definitions and a compressor. First, it's device.
Mateusz, I'm very sorry. I think something is with the voice or with the speaker. Could have this. Now it's better, I think, yes.
Okay.
Thank you. Perfect.
Okay. So first definition, a compressor is device reducing volume of the gas. It's simple.
No, I'm sorry. It's again. It's just something like moving. I don't know if other participant, if you can hear well, just drop a message in the chat.
No, we can't.
Yes, it was just a little bit muted. We felt that it was on the back.
It's to mute, yeah?
Yeah, it's a little bit like faded the voice.
Okay.
I don't know if the microphone was moved or something like this.
Here's my mic.
Okay. And if you try to be a little bit closer to your mic.
Closer, yes.
Let's try. Okay, let's try.
Okay.
No, we don't hear you. Oh, sorry. Let's try.
What can I make?
But now we can hear you good, I think.
Here? Yes.
Now, yes.
Maybe
yes.
Maybe it's good, better place for my.
Yes, exactly. That was perfect.
Okay. Okay.
Great, like this.
Once again, two simply definitions of a compressor. Now you hear?
Was when you before was really good. Sorry.
Okay. 1 2 1 2 1 2 3. Are you hearing me?
Yes. Yeah.
Yes.
Yes, like this is good. Yes.
Maybe I have to touch my maybe solution to switch here.
Okay, if you just try to be a little bit closer to the mic, I think it will work out. Let's try.
Maybe here?
Yes, yeah.
Okay, we can try it if it's something you want to try.
Okay.
So I start on the definition of
A bit closer. Sorry, Mateusz, I think it just feels like that it's far.
Raz, dwa, trzy, raz, dwa, trzy. In Polish is 1 2 3 1 2 3. Is okay?
No, yes.
Okay. Maybe I can try to use this microphone which is built in my computer.
Maybe just the microphone from the computer.
Okay, we can try it.
Okay. So sorry, everyone, just some technical technical pause before we go into
and
really
how?
heavy. Now it's good. Yes.
Is good?
Yes.
Is better?
Yes. Perfect. Yes.
Okay.
Yes, like this. Perfect.
So I just stopped the definitions of the A compressor. First is compressor is device for reducing the volume of gas. The second definition is device for lowering the inertial energy of the gas. Compression doing the work on it and giving air new features, predispositions to perform other work, like pushing a actuator piston. Next slide. No, here, no. Okay, we are here. Okay, sorry. So A compressor is a machine whose primary purpose is to compress gas. But a lot of electricity is transformed to heat. This graph, I think that you see similars in past, shows the distribution of energy in oil-cooled injected air compressor. The majority of the thermal energy available in the compressor is contained in the oil, and this is the place, this is the medium from where we recovered the heat. The second largest source of available heat not really is compressor air, but we don't talk about it today. Air compressors, high efficiency heating machines, of course, is not compressors low to reach a pressure level, of course. But despite your initial objection, I'm asking you today during this presentation, accept this, that the compressor is a highly efficient heating machine. Such that point of view will help you understand the rest of presentation. Of course, compressor low to the ridge level, burner or boiler work to reach a temperature or level. And to be honest, I have just said that difficult is in recovering heat from a compressors. The compressor doesn't care what temperature you need in this moment. You can get that which is available in this moment, and compressor doesn't care. It's not the burner, it's not the boiler. Doesn't care how many energy do you want to take in this moment. You can take only as much as is possible to available to take in this moment. So two kinds of ways of using heat from compressor. Sorry, I show this slide because sometimes I heard from my clients, we cover the heat from compressors, we have summer, winter dampers, and in the winter we direct this air after cooler to the production plant through the wall with a compressor room. In this point, I always mention a useful fact. Curiously, the balloons fly at the temperature difference about 60 degrees. Why I talk about it? Because think how this air can behave when it enter on the hull. This air after cooler have between 60 or 70 degrees. It will fly up to the roof and it will stay there. I talk about it because it's not effective way to use heat from air compressors. But of course, better as dispose it to the atmosphere. The second, in my opinion, only correct method recovering heat from an injected compressor is transfer the heat to the water and transfer it to the place, to the process of heat demand and use it there. On the left, you have some kind of external heat recovery unit. On this picture is power pack. It's not necessary in this place for us. On the right, you have a typical compressor with built-in heat exchanger. Built-in heat exchanger, please don't confuse it with heat recovery. According to the compressor manufacturer's instructions, only what you need to do is turn on a pump on the water side, and this is all. Is it really that simple? No, it's not that simple. and I will prove it in the next slides. Kruger-Dunning effect. I think that you can know this chart. Here you have experience and self-confidence. 12 years ago, when I was doing my first heat recovery from a compressors installation, I was on the top of the chart. But over the next 10 years, I improved my knowledge. I was already on the bottom. I see my cursor on the bottom of the chart. But my self-confidence is coming back because I learn this subject and I have knowledge supported by data. So 3 years ago, our company got a governmental grant to develop, test, and implement a universal device that can work with any manufacturer's air compressor, all-in-one plug-and-play device for heat recovery industrial oil-cooled air compressor. So, what our work consisted of? In first stage, we have to buy 27 heat exchangers for other manufacturers. In next step, we rented 15 compressor for 6 different manufacturers. They were from Atlas Copco, Kezer, Boge, Comper, the screw compressor, and vane compressor Matei and Hydroway. In 3 power ramps, 30, 75, and 110 kilowatt. And we tested this heat exchanger across these compressors. What does it mean? We test it on different flow of water side on the full temperature spectrum from 10 to 50 degrees. We measured the oil flow, used Coriolis flow meters. We measured the water flow, temperatures, oil and water sides. We get almost 1 billion measuring point, and we use it to create mathematical models of heat part of a compressor. In next step, we use this mathematical model, and through next 6 months, we tested 21 control methods of recovery. We rent 3 last compressor in the same range, 30, 75, and 110. And we okay, yes, is the moment in this 21 method, only one was turning on the pump on the constant flow, like in recommendation from air manufacturers. We have documented heat recovery over 90% of thermal energy, and or perhaps most important, we guarantee the safety of a compressor. Safety, we have some dangers. I will talk about it for a few minutes. What the effects of our laboratory work we have? First, the most important thing, we have knowledge supported by data. Secondly, we have already beta tested our device in industrial conditions. I'm sharing our projects with you on LinkedIn. Thirdly, the developed solution and methods of recovery are in process of being patented. We have positive decision from Polish Patent Office and PTC. Our publication already is public information. Finally, quite accidentally, for performing measuring, we confirmed the fact that electricity consumption was reduced by 6% in case of a pressure reduction of 1 bar. I said that we measure a lot of data. So pressure drop on the oil side. Heat exchanger on the oil side is resistor. It's of course. So why it's important to ensure a low pressure drop? The exchangers selected by us have a low pressure drop. Even with cold oil, the 30 degrees, we have below 15 kilopascals. The exchangers used by manufacturer have dropped between 40 to 100 kilopascals. Where it's important in changing work in compressor, when compressor is on load and go to the full load, when very low, very big speed compressor accelerate rotation from to 20% to 100%. During acceleration, the pressure drop increase to the second power. So if you have a big heat exchanger, you have low pressure drop, and then you can keep the same cooling condition like in compression without heat exchanger. I just talked about pressure drop on the heat exchanger. I will also mention on the pressure drop on the fuel valve at the same heat exchanger. The pressure drop on this valve is also between 30 and 100 kilopascals. It have to have much pressure drop to maintain linear flow control. So the total pressure drop on the exchanger and fuel valve set is between 1 to 2 bars. So in this slide, I show 3 pictures, 3 photos. At this one, we have compressor without heat exchanger. Our crew, our guys always make a photo of compressor controller before built-in heat exchanger. This picture under this first is the same compressor, and we catch the same moment of pressure average load of compressor. Here we have 70%, and here we have 70% too. The same pressure, the same temperature. It's not this the same picture. This progress circle is in the other place, and I ask my automatician to force full load of this compressor. This is a VSD machine. He make it by increasing the pressure. So now in that the biggest picture on the slide, we have a compressor in full load and heat recovery installation working. So in higher pressure and higher load, it's 100% load now, we have a lower temperature of oil. So you can get that result if pressure drop on this resistors, heat exchanger or heat exchanger and fuel valve is not significant. So I think it's all in this slide. It's I want to talk about some strange situation because fuel valve on the axle of the heat exchanger. I will pick on it a bit. Its function is very important. Its task is maintain the temperature above curtain temperature. Most often it's 55, 60 degrees sometimes. It's protect a compressor against overcooling. Its disadvantage is that without control, the energy received from compressor, without control of the water flow as function of oil exchanger outlet, the valve that is responsible for the compressor not overcool oil can be responsible for its overheating. What we have on the simulation, I need to give you some input data. Here we have a screen of controller, a compressor. We can watch here increasing temperature when compressor is on the load. Heat exchanger and of course fuel valve at this heat exchanger. Insert of this valve is 55. Here is a three-way valve integrated filter, the standard, which is built-in compressor. Its insert thermostat is 75. So what happened here? Water was overcooled oil, so temperature of oil was dropped, and I will show you inertia of this valve caused by valve at the heat exchanger. I will stop the simulation a few times and say something more about situation. Maybe stop. So as you can see, the compressor, the oil on the stage or in the separator is the same. Now it's 60. But this valve near radiator don't see them. Why? Because this warmer oil from the separator is mixing by this free valve with this overcooled oil from heat exchanger. And I will stop now again. So as you see, in separator you have 70 degrees, but this valve still don't see that because we still have this overcooled oil from the previous situation. So after 35 seconds, I need to, okay, pause. After 35 seconds, this valve can see this increasing temperature of oil. The state time is a parameter of Fourier valve. It said us how many time this valve need to have to make full move from full open to full close, or from full close to full open. Usually, this valve in compressor have state time 20 seconds. Increasing temperature of oil in compressor is 1 degrees per 2 seconds, or half degrees per 1 second. So difference between insert in this valve 55 and 75 is 20 degrees. So we have 20 degrees is the 40-second time in increasing the temperature of oil. So when this valve needs 20 seconds to make a full move, we have two enough speed valve. But if we make an inertia caused this overcooled oil in heat exchanger, this valve haven't enough time to open to the radiator. In that case, too warm oil. Oh, I have to go back. In that case, if this valve haven't enough time to open, oil could flow to the injection valve on the short circle without oil cooler, and compressor could be overheated. It's not impossible situation. I will show you it on the some recordings of our implementation. In this video, the heat meter show this in practice. Our clients have heat recovery installation from one compressor. They ask us to make installation from this one and second one, the same range, power range 160 each. And I ask my automatician to make me a movie, make me a record, the heat meters, but without algorithm controlling the temperature of oil on the outlet of the heat exchanger. So turn on a pump on the constant flow, and we try to watch what will be happen. So power is increasing. We have 320 kilowatts in both compressors. So here is nominal maximum power which we have in oil. In this moment, oil give us some credit, heat credit, and now we have a peak of the power. 99 no, here we have peak of the power, and the power drops because three-way valves bypass the heat exchanger. So the energy diagram looks like ECG. We have heat recovery, we haven't, zero power, etc., etc. Inertia, what kind of valve have an inertia? Only that kind which not exist. In our solution, we don't use three-way valve. We control temperature of oil through the controlling flow on the water side, and we keep temperature of oil on the 55 degrees level. So we haven't overcool it. We can flow the water when the water is warmer as oil. So we control it. And in that case, the temperature near the fuel valves near the radiator is the same with 1 second delay, like in the separator. And
So if I understood you right, you have a control valve on the water side, right? That controls the flow.
we haven't we don't use fuel valve on the oil side.
Yeah, on the water side, control valves or what exactly?
Though we have variable speed pump.
Okay, yeah.
And this is the same heat measure in the same simulation, but with using our power control algorithm. Nothing interesting will be happening here. And some kind of appeal. Attention, you can write down the greatest secret of the heat recovery. The most important thing is maintain full flow oil through the heat exchanger. If you can control the temperature of the oil on the exhaust of the heat exchanger, you can you have an inertia on this valve near the radiator. You can get as many heat as is currently available in this moment. Your compressor will be work well. One more dangerous connected with this free valve. I wrote several publications on LinkedIn about them getting stuck. The constantly operating fuel valve wears out on the question is not if, but when it will get stuck. In this implementation, the valve was stuck on the exchanger bypass. What does this mean? If it were not our automation and measuring system, the customer will thinking that he recover a heat, but they can recover nothing because oil is bypassed by it exchanger. Only that valve which not exist can get stuck. Coffee, 1 moment. So, something about control, enough about fuel valve. I can imagine situation, installation operating without control, working efficiency and safety for compressor, but only curtain constant in the real world is change. The exchanger was selected for specific parameters. What I mean, for nominal temperature of oil on the engine on the compressor and on the outlet. Nominal flow is known by compressor manufacturer, and the same on the water side. For example, oil 90 to 70 and water to 40 and 60. But if oil, when oil is warmer, the heat power of the exchanger is higher. So if power is higher, you can overcool oil. And different situation when the water have lower, higher temperature, the power of heat exchanger is lower. So in this situation, oil could be go to the radiator, and you will lose available energy. So this graph shows the response of the power control algorithm to change. The rate change of water flow as a function of oil is the same as the rate change of temperature on the oil side. You can think about use a controller, regulator, known use which is using in heating industry. So I don't recommend it because it's too slow. Temperature thermal change in compressor is very rapidly. A full circuit of oil from screw through separator, through a valve near radiator and injected valve takes 30 seconds. In heating systems, in domestic systems, hot water from the boiler go to manifold. From manifold pumps this water through pipelines 100 meters in one way. This water flow through radiator and come back to the boiler room. This circulation takes a few minutes. So changing the water flow in an incorrect way will cause oscillation in the operation of these two valves, and the compressor will work even worse than with a constant flow. So if you if you want to control it, you have to make it as best as is possible. But if you haven't this tool to make it, turn on the pump and make a constant flow. So some kind of sum. We have a large exchanger with a low pressure drop. We don't have a oil three-way valve, and we haven't pressure drop with connected with it. We have a circulation pump as an energy recovered executive element, a PLC controller with power control algorithm, a temperature sensor. So we have a complete heating device and the right heat exchanger in the box. So power pack and power control are fully functional heating device. The exchanger in compressor is just exchanger, one element that can create a system, just like a boiler without burner or burner without automation. Why is like that? Why don't compressor manufacturers support heat recovery? This is a question for them. I once heard from someone that he sold compressor with heat recovery system. So I explained to him that it was like selling a screw with motor on the pallet to the customer and telling him that he sold him an compressor. It's one part, one element of all system, but it's only heat exchanger built in compressor. So here I want to show you example of our implementation. This is the smallest compressor in our portfolio in heat recovery installation. Client have compressor without heat exchanger, and compressor was on the guarantee time, so manufacturer have to build in heat exchanger to the compressor. You can watch oil 100 degrees before built-in heat exchanger fuel valve. The same compressor worked at 80 degrees. So power control in action. 86 degrees. Heat recovery efficiency is the same. That installation, I make a screen from my phone. This installation gives us 21 kilowatt hour in 1 hour and 4 minutes. So this is a 77% efficiency relation to rated power. We are talking about GA26 VSD. So this is a variable speed machine that's not constantly loaded. It fluctuated in speed all the time. And I can take a public challenge. If someone have heat recovery installation with better result, I will fly to him, even to the over end of the world, and carry he or she on my back from for 1 kilometer. So many of my theory is some kind of appeal to compressor manufacturer. You cannot give a customer a heat exchanger and leave him to deal with it himself. You can't leave the designer without support on how it should work. On this project, designer didn't trust the compressor supplier. Designer designed variable speed pumps, the linear fuel valves, and on the water side, and reduced them to the rectangle with dashes line, on which he wrote PLC. He didn't know how to control it. He didn't know it. But the project was predicted mechanically that if someone knew that they can use it. So I swear the shortest part of today's workshop, power pack and power control, heating compressor recovery devices. Power pack is for machines without heat exchangers and in power range up to 110. Power control is pump group with power control controller for compressor with built-in heat exchanger up to 500 kilowatts. Examples of implementation. This implementation is from Brembo. Maybe you know, manufacturer of brakes. This red brakes in faster cars. For pieces of 110 kilowatts power pack, shut off, turned off 700 kilowatts boiler room. Power control, as I said, pump group and controller with algorithm power control. Of course, pump group is matched to the compressor power. And example of implementation from glass manufacturer. Client's compressor had exchanges, and with power controls together create a recovery system. Conclusions. Heat recovery from a compressor almost always pays off. It's an excellent way to meet emission standards, reduce footprint. Heat recovery with control guarantees the safe operation of the compressor and enables the declaration of specific saving result. And my favorite, investing in energy savings, not only for heat recovery, any energy savings. It's like paying for certain amount of energy onward at today's megawatt price. So if your clients have possibility to make this installation with simply payback time, for example, 2 years, and they don't do that for this time, for example, 2 years, they haven't an installation and this money because supplier of gas, supplier of electricity, or other medium will have it. Questions?
Great, Mateusz, thank you so much. I learned really a lot today, so I didn't know about this kind of problems. I see that we have questions in the chat, and please feel free to ask. Before we finish, I just want to tell everyone and invite everyone to our AirG movement platform. So this is basically what thanks to this, we're having this webinar. It's the platform where we are connecting experts in the compressed air field on the demand side, compressors, heat recovery, Mateusz. If you want to hold any webinars, you want to share also your knowledge, please let me know. And as well as for the end users that use this kind of systems and actually want to save the energy. So this is the platform where you can just register as a member completely for free. And then you can contact there directly Mateusz to discuss like further these things. So I left here the link, and I see this actually very interesting discussion in the chat. So I don't know, so it was from Robert. Robert, would you like to ask the question, or maybe you just read it and tell us? So
where's the first question?
So the first question was that Robert writing that we had to change the valve in the compressor because the startup phase caused overheating. The inertia was too big. We changed from 75 to 50 C valve. Do you recommend to change valve to lower C valve? This was the question from Robert.
But Robert, are you thinking about which valve? At the radiator or heat exchanger?
At the radiator.
Okay, but 55 near the radiator is too low insert because you can overcooled oil in the winter time. If you have too cool oil.
I know, Mateusz. This compressor is built with a frequency-driven ventilator also. So I do not think it's a big problem. Our problem was that at the startup phase, the inertia of the valve was too big, and before the frequency-controlled ventilator can work properly, the oil overheated.
Okay.
In the summertime, this is and in Hungary there's a 38 degrees, so you have to find some solution.
Okay.
to
make faster cooling the oil. Yes.
Yes.
Okay. If you keep a good temperature on the square, good is higher than 70. It's safe. It's safe temperature in compressor stage. If you have in that situation higher than 70 degrees, it could be some kind of solution of the situation. I had one implementation when client order our products and don't use this heat necessary is a pressure lever in pressure installation. And in the summer, we help a compressor radiator to keep temperature of oil in nominal level.
Absolutely,
So,
absolutely, I understand, and we recommend also to use heat recovery in the summertime, if not possible to use for process heating, then use a special fan and get rid of some kilowatts to help the compressor. And this is really interesting because this compressor is built in a container, and we have no problem at all after the startup phase. This is only for startup phase. We have no problem with the power consumption, no problem with the heat, no problem with the cooling of the compressor if works constantly loaded. But in a startup phase, we we have to found something.
You could have here two kind of dangerous situation. Firstly is the inertia of this fuel valve near the radiator, but second is inertia on the injected valve. One of both. But if you insert the lower temperature insert in this fuel valve and you have the effect, I think that you solve the problem in summer. But you have to control it in the winter, of course.
Absolutely, because it's not good to overcool the compressor in winter time.
Of course.
Okay, great. So are there any other questions? So just raise a hand and just ask the question. If it's not the case, we'll have this recording available. So we'll put in our...
Sorry about that. I would have a question.
Okay, go ahead, Robert.
Okay. What if the inlet and outlet temperature is not far away from each other? For example, in a heating system, there is for example 55 in, and you can get only 70 from the compressor, or maybe you have 60 in and 70 from the compressor. Of course, if I'm not mistaken, then with the VSD controlled water flow, you can adjust the water flow, and you can gain the heat amount, because if there is a constant flow pump in the system, you will lose some kilowatts. Is it right?
Yes, exactly as you say, but we in that case, as you said, when we have water to which on the inlet on the heat exchanger, we change the thermostatic insert in the radiator on the higher. If you don't do that, of course you can take some heat from the oil, but of course part of it will be losses and
okay, this is a really nice question, and as you answered.
If you have heat exchangers in heating industry, we design on the gradient on the 10 degrees. So if we have a water 60 degrees, we can cool this second side to the 70. So, but if you have 70 degrees insert on this thermostatic valve, so some part of oil could flow on the radiator, and of course you lose this energy. but you can exchange the insert of this Fury valve near at the radiator on the 75 or 80, and you can get all this heat. But of course, in consequence, in the summer and when you haven't need to heat, the compressor could work on the higher temperature.
And in the winter time also not. If you change the parameters to 80, then the compressor side will be 85 to 90, isn't it?
I think that 1995,
Okay.
1995 not so bad. 100 is dangerous because part of oil could flow with compressor air to the installation.
Yeah, like an oil vapor.
Yes, but it's specific situation. We talk about with client a lot of time when they have water over up to the 60 degrees, and we want to take all this energy what is in the oil.
Mm-hmm. Okay, thank you, but
Thank you.
thank you, Matos.
Thank you, Robert.
Okay, great. Thanks a lot.